Alrighty, y'all. Welcome to Chapter 6 here. We are starting with our first section. So we're going to be talking mostly about our standard normal distribution. Okay. And don't forget the awesome benefit of these online videos. You can pause, you can speed it up, slow it down, or rewatch it. So please take advantage of that. So I'm going to briefly explain what a standard normal distribution is here, and then we're going to take a quick break to discussing uniform distributions. Okay. So first, in general, what's a normal distribution? Okay. A normal distribution is our bell-shaped curve here, okay, where this value in the center is our mean. So a standard normal distribution is a normal distribution that has some specifics here. So it has a mean of 0 and it has a standard deviation equal to 1. All right, so in this chapter here, we are going to be discussing the correspondence between areas and our probabilities. Okay, so our distributions here is essentially representing our probability distribution. Okay, and we said all probabilities have to add up to what? Right, all probabilities have to add up to 1, right? Because this entire distribution represents every single possible outcome. Okay, so if you remember when we were talking about our significantly high and significantly low, I had before kind of, drawn down here and shaded this area in, right? So before we would say this value, this x value, is significantly high if this probability, right, the probability of x or more is very small, right? So when I'm shading this in here, I'm essentially saying that this area corresponds to probability. So that is our main sort of thing that we're going to be talking about in this section, right? That area, right, is equal to probability. So when we're finding area underneath our curves here, which typically we're going to be using a normal distribution or a standard normal distribution, when we find the area, it's going to find us the probability. Okay, so main idea there. So briefly, before I jump into our standard normal distributions, I want to come to our uniform distribution. So if you remember, we talked about uniform histograms in a few sections ago, maybe in chapter 2 or so. And a uniform histogram is essentially when all of those bars in your histogram are all about the same height. Okay. So in this section, we're talking about continuous probability distributions. So instead of having bars here, we essentially just have a horizontal line, okay? And our horizontal line is showing that the probability is the same over the entire interval of our x variable. So our x variable is our x-axis, right? P of x is our y-axis here. Okay, so we're saying over this entire interval of x, right, the probability is going to be the same. So whenever we're looking for probabilities in a uniform distribution, right? Well, in general, for any type of distribution, standard, normal, or normal distribution, uniform distribution, we know that our area, right, again, I'll write this again, our area is equal to the probability. Okay, so when we are looking for probabilities, we need to find areas. Our uniform distribution is very nice for us and is exactly a rectangle here. So when we're finding our area, the area is going to be this width of the rectangle multiplied by the height of this rectangle. Okay, and again, this whole area has to add up to what? it has to add up to 1, right? Because we said all probabilities have to add up to 1. Okay. So just to describe this again, so a uniform distribution represents our continuous random variable, right? Continuous means what, right? Continuous is describing a variable that has decimals that can go on forever, right? So like height or weight or length or time, right? You can be 6.23498 inches, right? So all of those are examples of our continuous random variables. And again, those create a uniform distribution if for all of the possible values, right, the probability is going to be the same, right? All right, so in general, when I'm talking about a uniform distribution, standard, normal distribution, all of these can be called density curves. I often just call them curves, right? So it could be for our uniform distribution, it could be for a normal distribution, it could be for some type of skewed distribution. Any of these are density curves. And for any of them, since they're representing continuous probability distributions, right, we know that the entire area under these curves needs to equal 1. Right. All right, so let's look at an example here for our uniform distribution. So let's say, oops, all right, so we're going from 0 minutes to 5 minutes here, and the wait time is going to be uniformly distributed. Okay. So our x-axis, right, is representing our minutes here, right, our x, and our y-axis needs to represent our probability. Okay. So the nice thing about uniform distributions is I have given you enough here for you to be able to figure out what this probability is, right? So we said that this entire area has to equal what, right? It has to equal 1, right? And how do we find the area of a rectangle, right? We multiply its width by its height here. So I'll just call this height h. So what is the width? Right, the width from 0 to 5 is 5. I'm just going to call the height h here. So how do we solve for h? Right, we divide by 5, so we're going to divide both sides by 5 here. So h is equal to 1/5, which is the same thing as 0.2. Okay. So this value here is going to be 0.2. All right. So an important comment to make at this moment, okay, is since we're in a continuous sense, we're in a little bit of a different place now than we were when we did our binomial distributions. Okay, so if I want to look at the value, this x value here, let's say this is 2.1543, etc. minutes. Okay, if we want to talk about what is the probability that some randomly selected passenger waited 2.1543 minutes, okay, what would we need to think about? We said that area, right, corresponds to our probability. Okay, well, if we're looking for the probability of a passenger waiting exactly 2.1543 minutes, we're looking at this line here. Okay, what's the area of a line? 0. Okay, so that means when we're dealing with continuous probability functions, the probability of one specific x value is always going to be 0. Okay, which is interesting here, very different than when we discussed our discrete probability distributions like we did in chapter 5. So the probability of any x value is 0. So that means for these types of problems, I'm not going to have you find the probability of a specific x value because that's always 0. I will ask you to find probabilities within some certain interval. Okay, so let's look at an example here. All right, so given this uniform distribution, right, which we just created for ourselves, we want to find the probability that a randomly selected passenger has a wait time of at least 2 minutes. Okay, so remember, area corresponds with our probability. So essentially in chapter 6, what we're doing is we're going to be creating pictures for ourselves, and we should be shading in our areas. So we want at least 2 minutes. So that's going to be 2 minutes or more. Right. So what we need to do is we need to find the area of this rectangle here. So its width is our distance from 2 to 5, which is 3, and its height, right, is 0.2. So we're going to get 0.6 here. Okay. So that is telling us that the probability that a randomly selected passenger needing to wait at least 2 minutes is going to be 0.6. A good point to bring up here as well, when we were working in chapter 5, right, there was a big distinction we had to make between the probability of x being greater than 2 and the probability of x being greater or equal to 2. Okay. So the question is, do we have that distinction here? All right, think about it. The answer is no, right? Because the only difference between these two x intervals is that this does not include 2 and this does include 2. Right? But what is the probability that a randomly selected passenger has a wait time of exactly 2 minutes? 0, right? The probability of any specific x value is 0, which means these guys are going to be equal to each other. Right? So I find this section to be a little bit easier because we don't have to worry about our differences between greater or equal to, or the difference between less than or equal to. We don't have to worry about it. Our main idea here is drawing a picture and shading it in. All right. So if you have any questions about the uniform distribution, please let me know. This is all I'm going to be discussing it. Really, for the rest of the semester, we're going to be focusing on our normal distribution. And in this section in particular, we're going to be focusing on our standard normal distribution. Okay. So again, a normal distribution is what? Right? It's our bell-shaped curve, right? So it's our bell-shaped curve here. The value of our mean is right in the middle, okay? And yes, we're using mu for our mean and sigma for our standard deviation because when we're discussing probability distributions, we're always dealing with the population. Okay. So again, our standard normal distribution has the specifics of the mean equaling 0 and the standard deviation equaling 1. Okay. So when we're looking here at our axis, okay, let's take 2 for instance, right? The value 2 is exactly 2 standard deviations away from the mean, which is exactly what a z-score is. So whenever we're dealing with standard normal distributions, all of these x values down here are really z-scores. Okay, so remember, a z-score, right, is the number of standard deviations away from the mean. Okay. All right. And again, right, this whole area has to equal 1, right, because our probabilities always have to sum up to 1 here. Okay. So we are now going to be finding areas or probabilities, right? Areas and probabilities go together. Okay. And I'm only going to teach you guys how to use the graphing calculator. I am not going to show you how to use the z-score table. If you're interested, feel free to Zoom with me and I'm more than happy to explain it. But for our purposes, I would rather we just stick with our graphing calculator here. Okay, so in the graphing calculator, right, we are going to go to the second and then vars, right, just like we did for our binomial PDF and CDF. Okay, and then you're going to select this second thing right here. Okay, let me show you in the calculator here. So we're going to go second. Sorry, the calculator is not working out for me here, but you're going to go second and vars just like you did with our binomials. You're going to go ahead and get the second guy here. So in general for chapter 6, we're going to be using these two. We're going to be using normal CDF and we're going to be using InvNorm. Okay. We will not be using normal PDF. We do not need that guy. So for right now, we are going to be using normal CDF. Okay. So in normal CDF, you put in a lower bound, an upper bound, the mean, and then the standard deviation. Okay. So, and again, this helps us to find areas, right? So make yourself a note of that. We're finding areas. And guys, I would really recommend still taking notes as we're going through this. I think it would be pretty helpful. So again, normal CDF finds us areas, right? Areas correspond to probabilities. So whenever we're trying to find a probability or an area, we're going to be using our normal CDF. All right, so let's look at an example here. So we're going to be talking about bone mineral density tests, and those are commonly measured using z-scores. And whenever these problems discuss z-score, you can assume that we are using our standard normal distribution, right, which has a mean of 0 and a standard deviation of 1. Okay. So let's look at an example here. With all of these problems, pretty please draw yourself a picture. Okay, the picture will help a lot, will keep you from making mistakes. Okay. So again, we're using z-scores, so we're talking about our standard normal distribution. Okay, so we are at a mean here of 0. Okay, and we're trying to find the probability. We're trying to find the probability that a person has a test score of less than 1.27. So which side is 1.27 going to be on? Right, our right side. Remember, our right side has positive z-scores and our left side has negative z-scores. Okay, so 1.27 is going to be over here. And let's see, we want less than 1.27. So we're going to be shading to our right or to our left? To our left, because we want less than 1.27. Okay, so for all of these problems, please draw yourself a picture. Right? Label your z-score, shade in your area, keep you from making mistakes. So again, we are using normal CDF here, right? Because we are trying to find a probability. Probability corresponds to our areas. Okay. So technically speaking, this is going to go on forever, right? So in reality, there's not really a lower bound here. But what we can do is we can use a huge negative number. Okay. I am accustomed to using negative 10 to the 99, right? You could type in negative 10 million if you wanted to. You just need to use a huge negative number. All right, so this is going to be our lower bound, right? So we have negative 10 to the 99, right? And make sure you're using the negative button and not the minus button, right? The negative button is right below the 3 there. So that is our lower bound, right? And then this area, we are trying to find this area all the way up until 1.27. So 1.27 is going to be our upper bound. So we have 1.27, okay? And what mean and standard deviation are we using? Right. A mean of 0, a standard deviation of 1, right? Because we are on our standard normal distribution. And guys, please try to answer the questions I'm asking you as we're going along. Try to mimic our class a little bit. All right, so plug that all in your calculator, right, and get an answer. Typically, we round to 4 decimal places when we're discussing our probabilities or areas, but you just need to pay attention to the directions in the quizzes and whatnot. Okay. So in doing that, we should get 0.8980. All right. So that is saying that the probability that a randomly selected person having a bone density test result below 1.27, right, is 0.890, 0.8980, right? So that is saying about 89.8% of people have bone density levels that are below 1.27. All right, please do this example now. So please pause this video and do this problem. And remember, draw yourself a picture, please. All right, so we're drawing our standard normal distribution because we're still talking about z-scores here. Okay, so a mean of 0, right? -1 is to the left, right? Because negative z-scores are on our left-hand side. And we want the probability of above -1 here. Go on forever. So again, we're using normal CDF. Right, because we are looking for a probability which corresponds to our area. We have a lower bound of -1, and then upper, again, technically, there's no upper bound. We just need to use a huge positive number. So again, I am accustomed to using 10 to the 99. You could just type in some huge positive number. Again, standard normal distribution, mean of 0, standard deviation of 1. Okay, so we plug that into our calculator and we're going to get 0.8413. So this is saying, right, the probability that a randomly selected person has a bone density of above -1 is 0.8413. Alrighty. Now, please try out this problem, right? Draw yourself a picture. Got to find your lower bound, your upper bound, and then you're plugging into the calculator. So please pause this video and try out this problem. All right. So again, these are all z-scores, right? So we have a mean of 0, standard deviation of 1. All right, which is smaller here, -1 or -2.5? -2.5. 0 is smaller than our -1.00 here. Okay, and we want the probability of between. Okay, so for this problem, they already gave us our lower bound and our upper bound. So in our normal CDF, we have a lower bound, -2.5, upper bound, -1, mean, and standard deviation. Okay. Make sure when you're doing these problems, right, that you're getting an answer that makes sense to you. Okay. First of all, normal CDF represents a probability or an area, so our answer should always be between 0 and 1, right? So if you get something that's not between 0 and 1, if you happen to get some sort of a negative, it may mean that you switched your lower and upper bounds. All right, so be careful there. The lower bound is the smaller number, the upper bound is your larger number. All right, so we put that into our calculator here, and we get 0.1524. Okay, also make sure that your answers make sense to you. Right, if we looked at our picture, it looked like that shaded area was probably about 15% of the total area underneath our distribution, right? And also for other problems, if your area goes over halfway underneath that curve, right, your area, your probability that you get by using normal CDF should be larger than 0.5. So please think about it and make sure that your answers make sense to you. Okay, so in general here, Okay, what we are trying to do is we are finding probabilities, right, by finding the area underneath our curves. Okay, so please don't try to memorize things. And again, we're not using our z-score table, right? We are using our calculator. But draw yourself a picture, shade it in, think about what's your lower bound, what's your upper bound, right? Your lower bound is going to be the smaller number, which is on the left-hand side. The upper bound is the larger number, which is on your right-hand side. All right, so now we are going backwards here. Okay, so the normal CDF type of problems, I would give you z-scores, and you would need to find these areas or probabilities. Okay, so normal CDF is for finding areas and probabilities given our z-scores or given data values. Now we're going to go backwards here. So I am going to give you areas or probabilities, and you have to find the z-score. Okay, so when you're drawing your pictures here, right, you're going to have the area that's shaded in, okay, and you're going to be looking for some z-score, some data value, or some data value. Okay, so again, please draw yourself a picture. Okay, draw yourself a picture. It will help a lot. So in our calculators, again, we're going to go to second and then vars. Okay, and we're going to go to this third one, invnorm, right, like inverse normal. So now we're inverting our problems here. You're going to input the area to the left, okay, the mean and then the standard deviation. A few of you may have the new operating systems for the calculators, and you may get to select whether you're putting in the left area, the center area, or the right area. So that's kind of a little benefit for y'all. But the rest of us, we always need to put the area to the left here. Okay. So let's look, oops, don't want to show you the answer to that yet. So let's go back here. Okay, if we want to find the z-score such that the area to the left here is 0.26, right, we would be using our invnorm. Okay, right, invnorm finds us z-scores or data values. All right, then we need to put the area to the left, right? This problem was nice and gave us the area to the left. And again, if we're talking about z-scores here, what kind of distribution are we using? Okay, our standard normal distribution, which has a mean of 0 and a standard deviation of 1. So 0, 1. All right, so enter that in your calculator here. And we should get negative 0.64. Okay. So we're getting negatives now. Why? Why are we getting negatives? Because we're talking about z-scores, right? So z-scores can be positive, can be negative, right? And 0 is our mean. Okay. So when you're drawing your picture and you're labeling here, right, we were looking for the z-score, you should also think for a moment before you go and use your invnorm, right? Think about, should my z-score be positive or negative? Well, if your area to the left, right, your area to the left here is less than 0.26, right, then your z-score must be to the left of 0, right? Because the area up until 0 would represent half of that total area of 1. Right? So this area of 0.26 is not going to reach all the way to 0 because it's less than half. So we should have expected a z-score that's negative. All right, so now let's see. I want you to find a z-score that has an area of 0.26 to the right. So please pause your video here. I want you to sketch your standard normal distribution, right? and sketch in where your 0.68 is and what our z-score that we're trying to find, right? Sketch where that is. Are we looking for a positive z-score or a negative z-score? All right, so let's see. This has an area of 0.68 now to the right-hand side. Okay. So if our area to the right here of some value needs to be 0.68, we must be past 0. Right, so now we're looking for some z-score where the area to the right here is 0.68. Okay, so our z-score should be negative. All right, so we're going to use our inv norm here because we are looking for a z-score. If you're a lucky person and you have the new operating system, you could enter 0.68 here and select right. For the rest of us, we need to enter the area to the left. Okay, so how do we find the area to the left? Well, we know that the total area has to add to what? It has to add to 1, right? So to find this area to the left, we can do 1 minus 0.68, right, which is 0.32. So our area to the left is 0.32. And again, standard normal distribution, mean of 0, standard deviation of 1. All right, so please plug that in your calculator, right? Make sure we should get our negative 0.47 if we're rounding properly. All right, again with these problems, please make sure that it makes sense to you. All right, now please do this problem. All right, so we have our standard normal distribution. We want to find the z-scores, right, plural here, that bound the middle 95%. Okay, so we're finding these two z-scores that bound the middle 95%. So this area here is 0.95. All right, so remember in our inv norm, okay, we can only put in the area to the left. Okay, so let's go ahead and find this z-score first. Right, we need to find the area to the left here. Okay. Well, if we do 1 minus 0.95, that's going to give us 0.05, which is the area on both sides here. Okay, but we only want the area to the left over here on this left-hand side. So we're going to have to take our 0.05 and divide this by 2, so 0.025. All right. So the area to the left of this z-score is going to be 0.025, and again 0, 1. Okay. So here we should get negative 1.96. Okay. All right, so what can you now tell me about this other z-score? Exactly, right? Completely symmetric here. Our normal distribution is completely symmetric. So the only difference between these two z-scores is one is positive and one is negative. Right, so our final answer would be negative 1.96 and positive 1.96. Right, these are the two z-scores that bound that middle 95%. Okay, and actually now think for a moment, this middle 95%, we have heard about this before, right? We talked about this 95% when we talked about our empirical rule, right? So our empirical rule was an approximation. It was saying that within, right, 1 standard deviation, they're 68% about, within 2, 95, within 3, about 99.7. Okay. Well, we just calculated exactly, right, that 95% of data is actually within 1.96 standard deviations, right, which is very close to the 2 that the empirical rule discussed. All right, so next here, we are going to talk about critical value. Okay, So a critical value is a z-score, right? Important here, it's a z-score that separates significantly low from significantly high. Notation-wise, we use this z sub alpha. Okay. So if we're looking at our standard normal distribution here, let's see, our z sub alpha, right? So z alpha, this is a critical value such that the area to the right of it here is equal to alpha. Okay. And remember, since we said that a critical value separates significantly low from significantly high, our alpha is always going to be an extremely small number. Okay, very, very small, like 0.05 or 0.01 or 0.025. Okay. So let's say that we want to find the value of z 0.025. Okay, so that value, that z-score is down here, right, 0.025. Okay, such that the area, right, this alpha is 0.025. Okay, so again, we are using normal CDF or INVNORM, right? We are using INVNORM because we are finding a z-score. Okay. So we are going to use our INVNORM here. Right. You have a few options, okay? One option is to find the area to the left of that z-score and plug that into your INVNORM. Another option that we have, all right, is to find the z-score over here such that the area to the left is 0.025. All right, and this tends to be my preference because what is the only difference between this z-score and this critical value over here? Right, the only difference is the one on the left is negative, the one on the right is positive. So in my INVNORM, I'd be plugging in 0.025, 0, and 1. Right. And here we would get negative 1.96. So now we know that this critical value, right, this z-score is equal to positive 1.96. All right, and we will continue talking about critical values more, especially as we get into our hypotheses testing. All right, but again, z-scores separate your significantly high, significantly low, right, which in the last few sections we used 0.05, but I had mentioned we could use other values as well. Right, so here we're using 0.025. All in all, our alpha is going to be some very small value. All right, so this was the end of 6.1. Please Zoom with me or email me questions or attend office hours virtually. All righty, thanks a bunch. Bye.